So welcome, I'm Cyrille Artho from KTH in Sweden, and here I'm giving you an overview of Java Pathfinder, basically what types of problems, especially the core, is good at solving, how it works, and what kinds of improvements people have made in the past. So the inspiration for Java Pathfinder comes from model checking, where we have a system that has a set of initial states and it has all possible sorts of behaviors. And these behaviors are basically evolutions of the system state over time, and that's called a trajectory. And what you want to make sure is that the system can't get into unsafe states where safety properties are violated. So a red trajectory that leads to such a state would be a counterexample to that. And model checking, as shown on this slide, has been applied to protocols or algorithms. So as the name says, it's typically for models of a system and not the system itself. And we can map software to such models, and this has been done successfully, especially for embedded software or device drivers. And with Java Pathfinder, the desire was to actually apply this directly to software. And that leads to software model checking. And the inspiration behind software model checking is, again, the state space search, where we search through all possible executions. And now I'm looking at the case of concurrency. Java Pathfinder can also handle non-deterministic data, so we could also have a choice over a value of a small integer, for example, 0, 1, 2, 3. And here I'm showing a very minimal example, so it fits on the slide, where we have two threads, T1 and T2. And if both threads are active and nothing else is constrained, we have two possible ways how they can execute. Thread 1 can execute first, or thread 2 can execute first. Now, if we test the program, we can only see one of the two outcomes. For example, T1 runs first, and if it has only one operation to make the slide small enough, it may finish then, and then there's only T2 left, and that one runs, and then the set of available threads is empty. Now, if this small program has a problem that only occurs if thread 2 runs first, we may not see that in testing. We basically have a 50% chance, or actually even less, because depending on the CPU load and the hardware and software platform, this may pretty much always be the default way how things execute. So what JPF does for us is that it creates a snapshot in this yellow state with the two threads active. It executes one choice, and then it backtracks to that snapshot. And in this way, it can try a different outcome of this choice, in this case, a different interleaving. And by exhaustively exploring all possible interleavings, it can find all possible program failures from this particular setup, from this initial state. There are some limitations on this, because you might remember from early computer science that the problem of whether a program is correct is basically undecidable in general. So this exploration, of course, might take too much time and not terminate. So that's the key limitation. So this works on programs with a state space that is not too big. JPF can handle a surprisingly large state space, but of course, it's still finite. And there are some other limitations, such as, for example, networking, that I will briefly mention later. Now, how does this differ from software testing? As I mentioned before, in software testing, we run only one execution, one trace. So if there is any random number or any scheduling, which is basically random as well for all intents and purposes, we cannot influence that, and we see one outcome. So in this diagram, I have the starting state of the program at the top, and then we have this red trajectory that goes down from top to bottom. And through this scheduling and other maybe random choices, we go somewhere in the state space of all possible executions, but we see only one trajectory. So we can test the program maybe 10 times if it's somewhat non-deterministic or flaky, but even then we will miss defects if there are some that are related to concurrency. And this way of testing is therefore never exhaustive, but it's scalable, so it can run relatively fast. On the right side, we see in principle how software model checking works. So it can explore all the traces that originate from this starting state and find all the defects, but it cannot necessarily explore them to the end. So depending on the search strategy, it might do breadth first or depth first, but you might not get the full triangle, you might only get a part of it. Another advantage is that you can also monitor the program behavior more systematically without having to insert assertions by hand. And I think in the afternoon we'll get a presentation about that. So it is more rigorous. It is in a sense inspired by formal methods, and you can consider it as such. It doesn't give you false alarms because it's based on the actual bytecode. So anything that executes is a real possible execution. And it provides you very detailed and nice execution history if it finds a defect. So it provides a full explanation. You can also use JPF without doing full verification. So one way to use it is, as I've just shown, that you explore all the states and you can actually prove for a given setup that the properties hold, but it's not very scalable. Also, the set of initial states might be too big, so you might only prove it for certain configurations. That's what typically is done. And the set of possible configurations might be another dimension that's too large. So you still often use JPF for fault finding. And you do this by restricting the thread schedules. As you have seen, we could restrict it to pairs of threads, as shown by Pavel. Or you restrict the initial states to certain sets of configurations that you suspect might be responsible for bugs, but of course there might be others. And then you can find bugs faster, as with a more exhaustive search. And it's still quite useful because even then it finds bugs that usually testing misses. And there has also been some work on optimizing heuristics, such as this older paper shown at the bottom. And when you try to guide the state space search, it may also even help to know what kinds of problems you look at. Because for a deadlock, you basically want to do the opposite as for a data race. For a deadlock, you want to go to states with a lot of locks being held. And for a data race, you want to go to states where few or no locks are being held. Now, how does actually JPF look like? It can do all these things, but I haven't shown you what it looks like. So it has a core that is basically an abstract virtual machine. So it implements its own JVM compatible virtual machine. It has the capability, of course, to load bytecode and the configuration. And then it has extensions that tell JPF how to execute this bytecode. And then from these executions, it generates reports, but it can also generate test cases. We'll see this in the afternoon with symbolic Pathfinder and try to mine specifications and so on. Originally, it was really only what I've shown before, this model checker for Java bytecode. But because it has been made modular and has this extension mechanism, it can now do more than that. So the project is now more than 20 years old. It started at NASA Ames, originally building on the Spin model checker, but then it has been rewritten. So JPF, as we know it, is really actually based in 2000, the code base. And in 2003, there was this big refactoring to make it extensible. And then the biggest step was in 2005, where NASA decided to make it open source. Or actually, the researchers, they wanted to make it open source much earlier, but by 2005, the bureaucracy in NASA finally caught up, and it was their first open source project. So this was really pioneering, and they had to put all the legal frameworks in place to make this possible. And now there is a webpage at NASA with probably more than 100 open source projects. So this is really grown. So this was also a very influential effort on the organizational level. Then in 2008, JPF participated in Google Summer of Code for the first time, and we've been included in most years since. So a lot of the development was sponsored by this Google Summer of Code. And later on, it moved to its own server, which was then replaced by GitHub user group where it currently resides. Over time, more than 20 universities have been involved worldwide. The community is maybe slightly smaller again now, but we hope to grow it again. And also, there are several companies that have used it. Fujitsu has even published a paper at the JPF workshop once. So at the moment, the main platform that we use is Java 8 compatible platform like OpenJDK 8. We have a version that supports 99% of Java 11, I would say, and contributions are, of course, very welcome to support newer versions of Java. It's quite easy to install. You basically clone it from Git, and then you run the Gradle wrapper to compile everything automatically. So all the other dependencies are automatically fetched. Here you can see how you can test it, and it has a complex way of configuring it, but that's maybe not so interesting. So you can later on look at the slides and study that or documentation. But now let's look at an example. So here I have a very contrived example. Of course, it doesn't make sense as a practical program. It's a hello world program that prints hello and world as two separate messages in two separate threads. And it does so by creating two threads that have this payload shown on the next slide, where the two strings get added to each other and then finally printed when the whole system is ready, when both threads are finished. So we can see that I start thread 1 first and wait for both threads to join. And if you run this, then you get this parallelism, which most of the time runs in the order in which the threads are started. So here I show an extended version of a UML sequence diagram, because sequence diagrams cannot show concurrency, where I first create the worker 1 and then worker 2, these two hello world threads. And in most cases, the first one gets executed because it's has been waiting for a longer time, and then the second one, and then we join, which means that we wait for them to finish their operation, and then we finally print the result. And the way this works in Java is that you create instances of class thread, and in the run method, you have the code. And most of the time, these threads run almost immediately. Sometimes the main thread gets a bit more time, depending on how many cores you have in the CPU, etc. Usually this thread runs first. So what happens if you run such a hello world program in your regular Java environment, the result will almost always be hello world. And it almost never gives you an incorrect result. The type of parallelism that is used in this simple example is sometimes called fork join, because the creation of the thread is sometimes from the Unix command where you fork a new process. It's called forking a thread, and then joining waits until that thread is terminated. So we never get an empty buffer or a half empty buffer, but it might happen that we get an incorrect interleaving. So here we see some explanation. So what happens now with this hello world is that the run method simply appends data that was given to the constructor. So we have a shared buffer. Both threads get the same buffer. One thread gets hello, the other one gets world. And to get the expected result, hello world instead of world hello, the threads really need to run in that order. Now, the thing is, if you test a concurrent program, it almost always runs in the right order, because the CPU is almost never that busy that for some reason a thread that was about to run cannot be scheduled right away. So if you do this in a regular JVM, then you get hello world. And you can do this 10 times, and it's almost guaranteed that you get 10 times the correct output. Maybe if you do it 100 times, it might deviate at some point. But testing is really not a very useful method here. But when you run with Java Pathfinder, you can actually see that we get these possible different interleavings as well. So as JPF explores the state space, it actually executes the system out commands and prints them on the console. So some of the commands are intercepted because they interface with the real system, but printing on the screen is just passed through, so we can nicely see that it explores different interleavings. We can also see that the number of times hello world is printed is, in this case, greater than world hello. This is for an older version of JPF, but this is because JPF tries to match equivalent states during the search. So at some point, it can figure out that it doesn't have to explore more interleavings where the two threads are reversed, so that these two are enough. And then it is able to explore fewer states and optimize this exponential search. The problem is that searching through all the possible behaviors is exponential in the size of the program, so you try to do your best to optimize it. For a program that's as simple as this, there would actually be more optimizations possible in theory. The optimization in Java Pathfinder is not theoretically optimal because it also supports constructs like share conditions with wait notify and a lot of other details in the bytecode for which you couldn't so easily apply an optimal search. And while this makes it slightly slower than theoretically possible for programs like the Danning Philosophers, for more realistic programs, it has a near optimal search that is also as precise and correct as possible. So now we saw that JPF is able to explore all these interleavings, and we see the output that gets generated, but we do not see how in detail this was actually generated if we get world hello. So we could sift through the log and actually observe in the first place that the output is not always correct, but this is not a good way. You might easily miss an incorrect output, and it doesn't really make sense to verify the console log against incorrect results of the computations. This is because to be useful, JPF also requires properties. So it needs to be told what to verify. And the simplest type of property is a safety property, which is written as an assertion. So you probably all know assert true and similar assertions from JUnit. So that is quite popular. In this case, we also write assertions in the test harness. So the assertions can be both in the application as a sort of consistency condition, if the internal state is correct or not. And if you write your own application, I really recommend you to put as many high quality assertions as possible into the application. The reason for this is if, for example, you get an array out of bounds exception, it's often much later than where the root cause of the problem is. So then the incorrect access has already happened, and the program may already have evolved from the original faulty state. And for example, if you have an array access with two variables, I and j, for a two-dimensional array, and there is some consistency condition, for example, I has to be greater than j, then if you put that kind of assertion, assert I is greater than j, into the program, and for some reason the indices are not looped over correctly, you will get an assertion failure right where this loop structure starts to behave in an odd way, and not as late as the array index out of bounds exception. So putting a lot of assertions in the program is not only good for Java Pathfinder, it's good for your whole program development and testing, because it tries to flag these problems earlier and gives you an exception quite close to the root cause of where things happen, and it's much easier to debug. So therefore, this is not really a burden to the programmers to have to put assertions, because it is something that they should be doing in the first place as much as possible. And if you have these assertions, then you can actually automatically verify if the output is what you expect. In this case, the assertion should be that the result of this operation, which is contained in the string buffer, should be equal to hello world. And now we can compare the output automatically with this expected output. And then what we see is that we now get an error that is reported by JPF. And the error is that there should be no on-caught exceptions, because any exception that is not caught at the top level results in the program aborting. And that's pretty much always an undesirable behavior, or at least it will be very user unfriendly. If the program doesn't bother to catch the errors and print a more human readable message, then we could also consider this to be a defect. And here is an assertion error, so that's definitely a problem that needs to be fixed. And then we see the location and line-by-line trace, which I'll show a bit later. And the trace, it shows all the threads that occur in the program. So we have a main thread that initializes the two worker threads later on, and I try to get the mouse cursor away a bit. Then we have thread 1 that adds hello to the buffer, thread 2 that adds world. And one problem is that you really need to watch out carefully for these thread numbers at the end of the transition. So this is a weakness in the textual output, that it doesn't visualize which thread runs when. You just can see it by this number. And this is also the inspiration why we want to use trace compass, because if you're not aware that there is actually a switch from one thread to the next, so if maybe transition 2 showed something about thread 1 or thread 0, then your mental model of the program will be off and completely wrong. So if you miss one of these thread switches in the textual output, you will reason about the bug in the wrong way and you will not understand it. And then you have to go back and eventually notice that you looked at the wrong number. And this is where I think the visualization will become very useful in the future, especially as it gets more powerful. So what I recommend is then to write these actions side by side, and then this allows you to understand the evolution, so that you make a large table and you write a summary of these transitions side by side. And from that, you can then provide a fix. In this case, the fix could be to have two join blocks to basically serialize the execution again. Now, I know it's a bit silly that I basically make the program sequential again, but it was just to be an example that's as simple as possible to show how JPF works. It's not supposed to be a realistic example of a concurrent program. And JPF supports pretty much anything related to locking, so I leave away the long explanation. If you want to look at the slides later, you can read that. But locks in Java are supported through the synchronize keyword, and the lock itself is basically any object instance. So you could create a separate object that you call lock, or even provide a class that has the name lock, but typically you would actually use an existing instance. So you don't need to create a separate locking object. That's maybe different from pthreads in C, where that's a separate data structure. But in Java, it's sort of hidden inside the object. So it's implicit. So you can write the keyword synchronized and then the lock. And the lock can be also a data structure. And in this way, you can prevent concurrent accesses to data structures that are modified or read in these critical sections. So the idea is that you have certain sections that even in a concurrent program are supposed to behave as if they were atomic or sequential. And to achieve that, you guard these sequences with a common lock, so that anytime a thread wants to execute this, it first has to obtain the lock, and then only then it can continue. And only one thread is able to hold the lock at any given time. So if there are two threads that want to go through this block of code at the same time, One of them will get the lock and then can continue, and the other one is suspended and has to wait until the lock is available again. When the first thread is finished, it will release the lock at the end of this block automatically, and then any other threads that also want to have this lock will be able to get it. Again, only one at the same time. And you can have cyclic dependencies, as with the Dunning Philosophers program. So if you have a thread that needs two locks, and one thread has lock A, the other thread has lock B, and they both want the other lock at the same time, then they cannot continue. So this is the responsibility of the programmer to ensure that their algorithm doesn't have any cyclic dependency, so you don't have a deadlock. The good news is, if there is a deadlock, then JPF will also find it. So deadlocks are another type of problem that JPF can find. And Oracle has a very good tutorial about concurrency. So if you're not familiar, then follow that link. I will make the slides available later. And then you can really learn more about concurrency in Java. Now for the deadlock, I show the Dunning Philosophers program, which I also showed in the visualization earlier. So the Dunning Philosophers has philosophers with two forks that symbolize the locks. And don't ask me why. So the story goes that these philosophers sit around the table and they need two forks to eat. So this is the strangest way of eating. Nothing, it doesn't really have any real life application, but yeah, they need to have both forks at the same time to eat. And the deadlock is if each philosopher grabs their left fork and waits for the right fork, and they're not smart enough to temporarily release the left fork, so they wait forever and they starve. Because it symbolizes a computer program, not humans, who wouldn't necessarily eat with two forks to begin with. So then we have this test harness that initializes the philosophers and the forks. And here we see that we have this very symmetrical pattern that gives rise to this potential deadlock where each philosopher might get fork I and then waits for fork I plus 1 next, modulo the number of philosophers. Again, if you run this in the regular JVM, you will not find a problem. It will pretty much always go through. If you run this with JPF, it will find and report a deadlock, and it will show that you have a violation of the not deadlocked property. So the property is always what should be the case, and we want that things are not deadlocked. So if the property is violated, then this means that the program has deadlocked. So we have to remove the negation here to see what actually happened. And then it shows the status of the threads. It's traditionally 5 threads, but it also works with fewer or more threads and some more information. And then we can see this history at the beginning. There's a lot of initialization, but this gives you a flavor now of what the error trace in the textual format looks like. So we see line by line how the program gets executed. So this is the first line of code in the main method where we initialize the array of forks. Then we fill it with new objects. And then later on, we start to initialize the actual philosopher objects. We also see this instruction without sources. This means this is part of the Java standard library. So this is not shown as part of the error trace in the default configuration. The rationale for this is that you normally look for bugs in your own program and not in the library. But if you suspect that it's the interaction of your own program and the library, then you can also configure JPF to display source information of the library calls. That would typically clutter the trace, so it's not done. And then at the end, what's very nice, if there is a deadlock, it shows a snapshot with the states of all the threads, including which lock it actually already owns and which lock it blocks on. So from this, you can actually see that there is this dependency. It blocks on lock 145, which is owned by another thread. And if you go through all the 5 threads, there's not enough space here, you can actually see that we get this cyclic dependency and hence the deadlock. Now, we can see from these examples so far that JPF can analyze very simple Java programs, which is nice. But how does it work in detail, and how can we actually go beyond that? The architecture of JPF is that it implements its own virtual machine for Java bytecode. And it also has other mechanisms to extend that. So typically, you would run the system under test, the SUT, on this JPF level virtual machine. And for programs like the dynamic Philosophers, that's enough. That's all that you need. But sometimes you want to access more advanced functionality, such as native code. The problem is that native code is written in C and it doesn't interact with JPF, so we don't know what happens. One way to deal with this is to build a so-called model class, where we re-implement native code in Java. And in that case, we can see what happens inside, and we can track all the memory modifications of the heap space and stack and so on. So this typically is a good way to do it if the native code is only written for optimization to make something faster. We are using an exponentially expensive technique to explore the state space, so we're not super concerned about making things a little bit faster. We want to be able to see everything. So in that case, model classes can replace native code. But sometimes you have no choice, like this print line that I've shown before. We want to actually see that on the console. So then you have to connect JPF to the underlying JVM, as JPF itself is written in Java. So it runs on the regular JVM, which is so-called host JVM. And then we have these native peer classes to build the glue between the bytecode that runs in Java Pathfinder and the underlying native JVM that can even execute native code like print line. This is not always convenient. So instead of having to write these native peer classes by hand, you would actually often like to delegate them automatically. And this is where extensions to JPF come into play. So I've shown them at the beginning briefly. And extensions usually implement some advanced feature. In this case, it's the ability to connect directly to this underlying host JVM. And that is implemented by the extension jpf-nhandler because it handles native methods. So the N stands here for native. And it can either ignore native methods because sometimes they do things that you don't really care about. It might just be some extra functionality. For example, it might be playing some sound. You wouldn't care about this when you automatically want to test the program. Or sometimes you really want to do it directly. For example, reading from a file, that you could then delegate directly to this native layer. And then JPF can in this way handle much more software than it otherwise could. So jpf-nhandler basically implements what I just explained. It's also available on GitHub on the same group as Java Pathfinder. It has its limitations, which you cannot work around in because there might be internal state changes inside the native code, and that you can still not observe. So you can only delegate the functionality, but there might be some things that are really important that happen in there, which you cannot really get by calling the method repeatedly without synchronizing the state. So it works for certain types of native methods, but not for all of them. One such native method that wouldn't work in that way is network communication. So if we were just to pass through the network input-output directly to the outside world, then we would modify the outside world and the environment and then backtrack and then, for example, send the same data again. So if we simply repeat the commands for output, we would send the same output over the network several times. In the best cases, we'll confuse the other applications if things are repeated like with an echo. Even worse, the input would be expected several times after backtracking. And that would not be the regular protocol, so the application would simply hang and wait for input again, which it has read before backtracking, and it's simply not compatible. So basically, we have this tree-like exploration of JPF by going through all the different schedules. But on the outside world, time goes linearly. There is no backtracking. So we can't save and reload in real time. JPF can do this for Java bytecode. So one solution to deal with this is to put a caching layer in between, which remembers all the things that happened on the network and then backtracks in JPF and synchronizes this correctly with the state of the outside world. The way this works is that first JPF runs, and at the beginning it only explores new states. So here we have state 1, 2, and 3. Every state is new, and we might do some output and input on the network. So for example, red might be a request and green might be a response. And at this point, because everything happens for the first time, we can simply pass this through and actually execute this also on the outside world. So for example, you could have a client that loads the Google main page, and we can simply pass this request to the Google server, which we obviously don't control, and this would work correctly. We'll get a response from Google. And what the cache layer does, it caches the data, the message sizes, and this mapping of the states from the program state to the state in the communication stream. If we then backtrack and try different interleaving, it's like rewinding a tape here on this cache structure. So we go back to position 2, both in the program state, because that happens by default, and in the state of this communication stream. If we then continue with a different interleaving, the cache layer recognizes that this is a redundant operation. And for example, we would not be able to read the response again from Google. If we contact the Google server for the main page, it has already sent the response earlier, and we don't get it twice. So what now happens is that the pre-recorded response from the first request is used from the cache, and that one is returned to JPF. And in this way, the state space exploration in JPF can continue without there being any problems. Now, there are some protocols where this has to be a bit extended, but I don't have enough time to show this in detail. Overall, the advantages are that this approach to networking, it's transparent to the model checker. So JPF doesn't have to actively synchronize with the outside world. This is done with this extension. It's scalable because only one program runs in JPF and the other programs run outside, so the state space is much smaller. But it doesn't support all the APIs for the network, and by design, certain types of applications like peer-to-peer cannot be supported in this approach. This could also be used for other types of I/O, for example, for file I/O, but there are already approaches if you only use a file from one process, by one process inside JPF. In that case, you could preload a random access array with the file contents and then use an array to symbolize the file contents. But for network I/O, you by definition have to handle multiple processes, so this iocache works quite well. It's not the only way to handle networking, though. There is another extension called jpf-nas, which is named by Nostran, who wrote this, but it also has some other acronym definition. So this modifies JPF so it can actually load multiple programs with multiple class loaders. By default, JPF can only handle one process with one main method. And it's not so easy to combine this to handle multiple processes. So there are different ways to do that. And the most efficient way that JPF supports is with jpf-nas. So you then have one class loader per application. This is necessary so you don't mix the bytecode of different processes, which might not be the same. You have a scheduler that is aware of having multiple processes, which optimizes the search, and also a network library that then connects these multiple processes so they can actually still communicate. This is really nice because you don't have to modify the application. You only have to modify the configuration file. So you maybe have to modify, write 5 or 10 lines of configuration code, and then all this works very nicely. Of course, with this approach, you extend the state space from one application to usually at least 3. Most of the time you need 1 server and 2 clients. If you have only 1 client and the server, there's not much concurrency. There's no concurrency between multiple clients if you have a single client. So you usually need to go to at least 3 processes, and therefore the state space tends to get very large, but it works for small networked applications. So, and it also works in some cases where the caching approach cannot be used for certain types of peer-to-peer behavior where there is state that is influenced in a way that you cannot observe just through the network communication. Then jpf-nas is still applicable. But by design, it's less scalable because the problem of the state space is that it's exponentially large. So if you add more processes, then it gets larger. But it's often the only way to do this. So even if it's not so fast, this is the most general solution, and there's often no other solution other than a completely different approach like theory improving. So there's no other automated solution to this. And one example of what you can analyze with such network extension could be a chat server. So here we have a main server that creates 1 worker thread for each accepted request. And then we have a single threaded client. And if you look at this, this is pretty much as simple as it gets while still being interesting, because a server should have some parallelism to be responsive and fast. But if you have 1 main thread in the server and 1 worker per client, then we already have 5 threads. So you can see that the state space becomes really huge. And we have used this program in teaching sometimes, and you actually have to limit the communication protocol to the absolute minimum. So you have to remove any complex messages that concatenate strings and have some internal overhead, and really strip it down to the bare minimum. And then you can run it for certain buggy configurations, and you find defects within 10 seconds to 1 minute. But you cannot analyze the full state space anymore, because if the exponent is 5, then it's just too much for the limited time that you usually have, and also the limited memory. So logically, what happens now with this extension jpf-nas is that it doesn't completely merge it, but it handles everything in JPF as 1, and it still keeps information about the boundaries, so then JPF can be applied. Okay, here, sorry, there's a repeated slide with the link in case you want to download it. And here we see what the configuration looks like. So this could be also for other client-server programs, that the server is 1 target and then the client can be another one. In this case, the client itself is multi-threaded, so there's no need for more than 1 client to have some concurrency. And then you also have to specify which process runs first, because this is important so that the server goes first. If the client runs first and no server is ready, the client will not be able to connect to the port and will just fail. And then JPF will report a failure of the client as an error trace. But that's a completely uninteresting failure, because we all know that from time to time we can connect to something and that fails. That's not news, and that's not a problem of the software, that's a problem of the timing or the network. So these tools to handle networked I/O, they have a built-in mechanism to avoid this, because otherwise we couldn't find the real bugs. And now if we have the trace from JPF, we actually get a huge number of threads. So I was saying before that we get 5 threads, but this is not quite accurate. We actually get 3 main threads from all the processes, but then internally in jpf-nas, it also generates these finalizer threads. Most of the time they don't do anything. They simulate what happens if a process is finished, and In that case, all the connections and files are automatically closed. So we can usually ignore these, but they do increase the potential state space a bit more. So instead of 5 threads, we actually get 8 threads starting from 0. That in the worst case makes the state space really quite tough to go through. To summarize, it is extremely difficult to use concurrency in an unrestricted way. If you use regular software testing, even with a good test suite, you usually have a very small chance to find most concurrency bugs. There are some that you might find right away because typically there is sort of a default timing that you execute in your software when you run it on the regular JVM. But beyond that, you will mostly be blind to concurrency problems. So therefore, we want to have a tool like Java Pathfinder that systematically explores all the possible interleavings. And in my experience, it works well for small programs if you sort of distill the essential algorithm of a program into a small example. So if we remove everything else that is complex, other functionality like business logics or interfaces with other tools, and you just run the core program, then you're able to analyze a lot of interesting programs. And through using JPF, you will also develop a mindset how to mentally reason about this interleaving. So I think it's also a great tool for teaching concurrency. Because usually when students start learning about concurrency, they are very optimistic and reason about the regular path that passes in the test. But they haven't got experience with reasoning about adverse timings that break their program. And if you see the error traces by JPF, then you start to learn what these traces look like. And then you really start to be able to think also in a way that makes you a better programmer for concurrent code. Even if you later write programs on a different platform, for example, in Go or in C, you will still benefit from this know-how about how to reason about concurrency by having used JPF. And JPF is therefore a great tool to analyze concurrency. And thanks to the extensions, there are also solutions for network software. Of course, there are still problems to deal with the scalability and native code, and those cannot be solved for all types of software. But it's great to verify, for example, a prototype where you look at the communication architecture and the synchronization between threads or processes to make sure that you don't have something that suddenly deadlocks or fails in some other way. And what I would recommend is that when you use JPF, you first do good testing. You need test cases in the first place to run JPF. So if you haven't done the homework and don't have any unit tests, start there. You also want to do a certain amount of system testing because unit tests don't cover everything. And once you've done that, then you can run some unit tests that may have some concurrency in JPF for one process. And later, if you really want to check networked applications, then you can use this net-iocache or jpf-nas also to check simple configurations of network software exhaustively. And we have found problems in network software. For example, there was a GUI for SCP that would sometimes crash when there's a timeout. And that was, for example, also one thing that we were able to run with such a network extension in JPF. And then we had a lot of algorithms where we seeded bugs that are realistic bugs, for example, in a chat server or in a download client. And we were also able to use JPF to confirm it. With this, I come to the end of the tutorial. We still have a few minutes for Q&A, so please ask if you have any questions.